In the last couple videos, we worked with or used some of these properties of integrals that I have up on the board here. And as I mentioned, it's a good idea to just formally state them. And although I'm not going to formally prove them, I do want to just talk through why they're true. So the numbers here are the numbers that these statements have in your textbook for easy reference. Okay. So property 6 is that the double integral over a region of f plus g. So my height function is a sum of two functions. Well, I can just integrate f over d, integrate g over d, and add the results. We took advantage of that in the last video where we had x plus 1, and we integrated x, and we were able to use symmetry there, and then we integrated 1, and we used property 10 there to do things. And at the time I said the reason we can do that is because this sum property is true for single integrals. And a double integral really does just have us doing two single integrals. One on the inside where we're holding one variable constant, and then the integral of one variable that we get after doing that. So if we can do it for each of the single integrals, we can do it for the double integral. Property 7 is similar. Oh, I should have said here, f and g are integrable functions. So we're supposing that these integrals exist. And here c is representing a constant. So if I have the double integral of a constant multiple of a function, I can just integrate that function and then multiply by that constant. And again, that's true because I can do that for single integrals. So I could pull the constant out of the first integral, then I could pull the constant out of the second integral. I've just pulled it out of the double integral. 6 and 7 together give me that we can also distribute integrals over subtraction, because subtraction could, of course, just be written as adding the opposite. So your textbook doesn't state the fact that integrals distribute over subtraction as a separate rule, but that follows from 6 and 7. So just like with single integrals, integrals distribute over addition and subtraction. They do not distribute over multiplication and division. All right, property 8 says if I have two functions and on my region D, f is bigger than g. Well, when I integrate f, I'm going to get something that's bigger than g. Bigger height is going to give me bigger volume. Okay. And that's true even if I allow for negative heights. Okay. I might be talking about f is bigger than g because it's less negative than g, but then I'm going to get a bigger volume in the sense of a less negative volume. Okay. So that property is true. We used property 9 when we were integrating over a diamond. I may have a region that by itself is not type 1 or type 2, but that I can break up into pieces, where each of those pieces is either type 1 or type 2. And as long as those pieces don't overlap, so that I'm not counting any of my signed volume multiple times, then the integral over the entire region is just the sum of the integral over the parts. Property 10 is what we established, that if you attach a constant height of 1 to points in your region D, then the volume that you're getting is just the area of D times 1. Numerically, that's going to be the same as the area of D. Of course, the units would be up. Area would be in square units. If I'm thinking of this as the result of the integral, I'm thinking in terms of cube units. But the number that I get is the number that I would use to measure the area of D. Okay. All right, and then 11 just says if I have a function that has a lower bound and an upper bound, those are just numbers where the lower bound is always less than or equal to the function, and the upper bound is always bigger than or equal to the function. If that's true on D, then I can basically apply property 8 a couple of times. Integrating this would be less than or equal to integrating this, would be less than or equal to integrating this. But of course, if I integrate the constant m, I'm just going to get m times the area of D. That's just taking a multiple of what I'd get if I integrated 1. Okay. And same thing for big M. If I integrated that, I'd get big M times the area of D. Okay. So we'll be using these properties, and I think a lot of them follow from a combination of common sense and our understanding of single variable calculus, but it's definitely worth stating them. And if any of them don't make sense or don't feel right to you, spend some more time with them. And if it still doesn't feel right, make sure you contact me in office hours. We'll be using these properties a lot as we're evaluating integrals.